roughly about 40 years. So we about 10 members worldwide. I think in terms of the number of members, the top 10 of the societies within the IEEE. So our officers at the PELS Administrative Committee are like this. Professor Liu Chen Chang, he is the present president for 2022-2023. He comes from Canada as an academia. And our immediate past president and the nomination chair is Freddie Blabjerg, professor from University of Aalborg. So he was the senior past president, rather immediate past president of the PELS Society. The senior past president and the Long Range Planning Committee chair is Alan Mantooth. So they have they are still active member of the PELS EdCom. Then we have officers of the PELS EdCom. So we have different under the president, there are different vice presidents. So we have vice president for technical operation, Patrick Wheeler from UK, University of Nottingham. We have vice president products, Brad Lehman, who is the president-elect for the next year. He will be taking it over from 23 onwards. Mario Pacas is the vice president global relationship. He comes from Germany. And vice president conferences and meetings is Jian Shen from RPI at USA. The vice president for membership and chapter development is Mark De Hong from Zhejiang University in China. And vice president standards is Johan Ensley. Now, normally people ask this question, and many of you are student member of IEEE. So people ask this question that why should I be a part of IEEE? And my answer to that is you start with a student member, and as you grow, you could be a member, then a graduate member, then member, senior member. Ultimately, that's the maximum level. After that, the last stage is the IEEE fellow. Now, by being a member of the professional society, it brings in recognition to you. No matter whichever part of the world you go, there will be an IEEE there. And being a part of it, you always enhance your technical knowledge if you are in the academic domain, or even if you are in the industry, the latest technology that comes along the way in the form of the standards and everything. Industry people develop all these standards and contribute significantly. So if you are a member, you have membership benefits like you are entitled to have publication, print, electronic or digital subscription for the different magazine like IEEE Power Electronics magazine. There are different transactions that we publish, Power Electronics, selected journal of the emerging and selected topics in Power Electronics, and the list goes on. Now, you could say that if you are a student or you're academic, your university has all these things in their library. Yes, for that matter, that's true. But if you graduate from the university and go outside, then you may not be able to avail all these things. So by being a member of the IEEE PEL Society, you can get the vast resources at your hand and you can access it. And that will improve your technical knowledge domain, and that is how it would be very helpful to you. Now, the other benefits for the member include if you are a graduate member and you are working towards your PhD degree, then you need to publish. And you publish in conferences, you publish in journals, all these things. So when you attend a conference or a workshop, and if you are an IEEE student member or for that matter IEEE member, you get discount. As a student member, you may be paying how much, about 10 or 15 US dollar per year. But once you attend one conference, the discount that you will get will range somewhere about 70 to 75 to 100 US dollar. So by attending one conference per academic year, you can regain the discount that you get from the conference, attending a conference. Your membership fee will be already taken care of. So that's one of the benefit that you get by being an IEEE member. Then we have a vast resource centers where all the multimedia online library, all these things are available, and you can have access as a member to those things, and you can download materials from there for your own reading. Then we divide the Power Electronics Society into different areas of interest, and we call that as the technical committees. About 3 to 4 years back, we used to have 7 technical committees, but I'm glad to inform you that as of last year, we have grown from 7 to 12. So these are the bullet point are the list of the different technical committees. And the very last one that you see, energy access and off-grid systems. I'm chairing that particular thing, and we organize the event for the student called as a Empower Billion Lives. So EBL1, we had already done it in 2019, and we are now in EBL2, that already ongoing, and the evaluation process is ongoing. And next year, March, the winning team will be announced during the APEC conference in 2023. So you can be a part of being a member of the IEEE PELS. You can be a part of this technical committee and then get access to various activities they do run. These are the networking. So we have about 208 chapters. Having said that, as I say, we we have 2 more chapters being formed within India, one under the Madhya Pradesh section, and the very recent one is the um, yeah, IIT Guwahati section. So we have 2 new PELS chapter that has formed. So we have gone to about 210 now worldwide. And young professionals enjoy various networking facilities, whether it is the Applied Power Electronics Conference or the ECCE, the flagship conference of the Power Electronics Society, be it in North America or in Asia or in Europe. We have various networking events where young professionals network, students member network with each other and benefit from this particular conference. Member participate in technical committees, conference committee, chapters running. And this is another point I wanted to bring it out, that IEEE not only provides you the technical details, but on the side of it, it also gives you the scope to grow yourself as a leader. So as a student member, if you're organizing an event, it tells you how to organize an event, how to plan for it, and how to make it successful. That could be a small student branch chapter event, or it could be a workshop, or it could be a conference. So being a part of the IEEE, you can be a part of all these different activities we run, and indirectly you gain the experience of organizing event and make it financially successful. So the management training program that you gain on the side of it, for which you don't pay any fees, but through the process you learn, and that helps. We also, I see a lot of women in the participants. So there is a women in engineering event and social gathering, and there are mentorship events. All these things are there. These are the distinguished lecturer programs. So as you are hearing this, we classify the distinguished lecturer as a class of 2021-22, but I belong to the class of 22-23. And we have grown the distinguished lecture from about 5 in the past few years to almost 10 this particular year. And that is because of the COVID. There are a lot of distinguished lecture like this one is being presented online, and it doesn't cost anything. except the internet that you use it for this thing. So the number of technical presentations, webinar, and everything has grown exponentially. And we see more and more requests from student branch chapter and the chapter. So that's why we have increased the distinguished lecture program from 5 to 10. Not only this, I also proposed and we have instituted the regional distinguished lecturer, because the distinguished lecturer can come from any part of the world, and for them to travel, the whole idea was for this distinguished lecturer to visit the organizational unit, that is the student branch chapter or chapter, and physically present this distinguished lecture, interact with the members and the committee people there, so that uh, they the power electronics domain knowledge is being disseminated to all the members. They cannot afford to come and attend conferences, and at the same time promote power electronics technology. So we have implemented the regional distinguished lecturer. As you know, IEEE is divided into different regions, and India comes on the region 10, and I am the coordinator for the region 10 for the Power Electronics Society. So if you go to the Power Electronics Society, besides the distinguished lecture program, you will find a regional distinguished lecture program. The idea behind that is people don't need to travel all the way from North America to India, or for that matter, Singapore, to come and give a distinguished lecture. We can invite people in the region 10 from Korea, from Japan, from China, from Australia to come and give a talk in India. And that is not very expensive because you are traveling only in the 6-hour flight zone. Uh, that will reduce the cost, and the number of distinguished and regional distinguished lecturer increases. So they can give more talks basically. So by the way, what I'm trying to say, the regional distinguished lecture we have already instituted. You can visit the website and you can invite people to give this regional distinguished lecture, either face to face or online as well. Educational student activities, as I said, we organize various types of challenges for the student competition. So IEEE Future Energy Challenge is one. We provide students travel grant, mentorship. Then there is a mistake here. It should be IEEE PELS PhD Thesis Talk Award. So PhD students give a 3-minute video presentation. It is archived, and then that goes through the competition, and there are awards given to that. Standards are mainly for the industry people, and they follow the standard or develop the standard, gives the test procedures for any product to come and to be marketed. So the home society, so IEEE has the new slogan, that is the transportation electrification community. So it's a Power Electronics is the home society which proposed for this one, but it is not just Power Electronics, but these sister societies like Power and Energy Society, Industry Application Society, Industrial Electronics Society, and Power Electronics Society. These 4 societies come together and managing the IEEE transportation electrification community. It is already written on the wall that the present transportation system 1.0 is not sustainable. That is ICE engine-based vehicle. All the ICE engine-based vehicle will be replaced with electric vehicle. It's just a matter of time. In Singapore, we have already planned and announced that by 2030, almost 30% of the vehicle will be electric vehicle, and by 2040, 100% vehicle would be hybrid or electric. No ICE engine vehicle would be possible on the road in Singapore by 2040. So that type of the aggressive plan we do, not just Singapore, all over the world. This is all ongoing in order to save energy, make the transportation more fuel efficient. And I'm glad that the Power Electronics Society is the home society for this particular activity. So fuel your career and your future. So join the IEEE PELS Society today and be connected with the ultimate source of power in your industry. And I'm glad that by attending this IEEE-DL, there is a promotion code. Dr. Hawk would be able to give that one to all the participants of this particular conference, and you can avail a 1 year free membership just for the first year only and new member only. Then be it student, be it member, or be it senior member, anybody who is an IEEE member, they can avail this facility and use the promo code and be a member of the PELS Society. I think with that, yeah, these are the contact administrator rather there. So we have various administrator for various activities of the IEEE PEL Society. As you see, almost 7 people are there. It is led by Mike Kelly, who is the executive director, and they follow different administrative role of the PELS Society. So join the PELS today and become empowered. I think this is a little bit old, $25 full year membership fee, and for the student it is $13. But come now you can get it free by attending this particular talk. But come 2023, this full membership will have a new category called essential member, and that will be brought down from 25 US dollar to about $10, if I'm not mistaken. That will be announced eventually. And this $13 will be brought down to about $6 or $8 for the student. So $6. I mean, I don't know how much a McDonald's burger cost, but in Singapore, a McDonald's burger costs $5, or meal if you take it is $7 to $8. So one McDonald's meal you sacrifice, and then you be a member of the IEEE PELS as a student member, you can get lot of information in the technical domain. But having said that, you have to sacrifice a little bit. But the cost, we are trying to bring it down as far as possible because we want to grow the membership and people to know about power electronics. So our present membership stands at about 11,000 plus. We want to increase to about 15,000 by 2025. And this is one of the way, by giving distinguished lecture and providing some of the free membership, hoping that they will continue eventually to be a member of the PELS Society. So these are the various things. Empower a billion lives. That is a very grand challenge. And I'm glad to inform you that in 2029, IIT Bombay won the first grand prize, almost $1 million for that thing, and that was for solar lanterns that has been marketed all over India uh, as a part of the company there. But it started from IIT Bombay, and my own student from Singapore, they didn't win the student competition, but in the regional level at IIT Madras, they own the regional student category competition, and they got about 4,000 US dollar as a prize. My own PhD student from Singapore. I think that's all about PELS, and I stop it here. Take a brief pause. If anybody has any question about IEEE, you can ask now. Dr. Hawk, what do you think? They can ask now, or we have to wait until the end?
We have kept a question answer session in the end, so I think.
Okay, fine. That's fine. Then I proceed further. So the responsive grids for future energy systems. Now, if you ask yourself a question, why do we need energy? This, when I teach to the undergraduate student, I ask this question, and I give the example that as a human being, in order to be alive and to do something meaningful, we need energy in the body. And how do you get it? You take food, you digest it, extract the energy, store in your body, and then use it as and when you need it. But body energy, if you use it extensively, you get tired and you cannot do many other things which you'd like to do. So we have come up with various types of machines to provide us or convert energy from one form to the other form and provide us the comfort to live what do you call in a meaningful way. Take example of transportation. If you have to go from point A to point B, do you walk? The answer is by and large, no, not necessarily depending on the distance. Even if the distance is less than a kilometer, if I have a scooter or a two-wheeler or a car, I will drive. So the point is, we are so used to have a comfortable lifestyle, and the more comfort we need it, the more energy we need it. And to maintain our standard of living, the amount of energy we consume has grown significantly over the years. And if you have seen, it is almost exponential. So when something grows exponentially, the demand for energy with respect to the x-axis on the time, if it is exponential, it becomes tangent. And with a particular year in future, it may not intersect. So you don't have an operating point. So we need to manage uh, how we get the energy to maintain our standard of living. And at the same time, can we come up with new sources, new ways of getting the energy in more cleaner form rather than using fossil fuel? And that is what is talking about responsive grids for the future energy systems. So the grid, utility grid has to be responsive. Present standard utility grid is unidirectional. You centralize power station, you burn fossil fuel, produce electricity, and directly give to the load center. So it is unidirectional. We want to develop microgrids where grids are not possible in remote location. For example, in remote location, mountain area, it is not possible to have the utility grid, so you develop microgrid operating in islanded mode. Then the loads. In Singapore, we talk about buildings. So the building itself is taken as a load, but it is connected to the utility grid. So the building as a load must be responsive. So if you make all these things, the generating sources, centralized or distributed generation, and the load, all them responsive, then we do grid edge GIS integration to meet all these demand. So this is what is my thought process for the futuristic energy system. I'm giving an example from Singapore context. The challenge of mitigating the carbon emission in Grid 2.0 of Singapore. As you all know, the climate change, the temperature is, rising very high in India. Yesterday, I was reading the newspaper that the northern part of India, the temperature this year is almost the highest in the last 120 years. That is because we are over consuming energy from the fossil fuel, and that is causing the global warming and related issues through the carbon emission. Now, in Singapore context, this diagram tells you that the red graph, which is linearly rising, that is the total electricity generation in Singapore. And the green graph that you see, so x-axis is the time from 2012 to 2020, a very small area. That's why it is linearly rising. But if I expand the time for few decades, then you will see it is exponentially growing for any country, basically. Most of the country, I would say. Um, the green graph that you see is the emission rate in kg CO2 that is emitted per kilowatt hour of energy. So this is one of the KPI. So we want to consume more energy. And if you want to consume more energy, the grid emission factor, we must maintain it. And we have reduced in Singapore from 0.4772 in 2012 to almost 0.4224 around there by 2015, 2016. I don't have the data for the rest of the year, but it is somewhere around there. Now, why the grid emission factor is going down when you are using more electricity generation? The answer to that is, in Singapore, we use fossil fuel to produce electricity. As you know, Singapore doesn't have any natural resources. We import everything. So the natural gas we import from Malaysia and Indonesia through the pipes, we run the power plant here. We used to have some coal-fired power plants, but those have been taken out. And 95% of the electricity generated in Singapore today is using natural gas. 95. The rest 5% are coming a little bit from solar energy and the waste to energy extraction. So since we are using the cleanest form of the fossil fuel, the grid emission factor has dropped. But the blue line that you see, dashed line at the bottom, around 0.4175, even if you use 100% natural gas, the grid emission factor cannot go below 0.41, and Singapore has already achieved close to that. That's the saturation point. We can increase from 95 to 97 or 98, but what's after that? How do you reduce the grid emission factor? And the only way to do that is by tapping on the renewable energy sources. And as I said, Singapore being closer to the equator, we don't have wind, unfortunately. So wind energy we cannot tap on, but fortunately we have solar, even if it is diffused, so we can put solar panel to electricity. And that is what we have planned, and we are doing it now. So by having photovoltaic generation, the grid emission factor can be reduced from the factual barrier that is there. And we have implemented several ways, all the rooftops and everything. The other problem for Singapore is the land area is fixed. It is 525 square kilometer when I came to Singapore about 30 years back. Now Singapore is growing horizontally. How? We are reclaiming land from the sea by putting sand. And from 525, we have gone roughly about 750 square kilometer, but we cannot increase that. That's why you see all high-rise building in Singapore, multi-story building. So even if we get sun, where is the space to put the solar panel? We don't have space. All the rooftop of all the buildings, even if we do, we cannot get more than 20% of the solar energy or the total energy consumption. So we are planning to go about 25% solar energy, and we have exhausted all the land space. So we are going to the reservoir, and we have solar panel, floating solar panel on the reservoir water. We have even gone into the sea, seashore, and put solar panel on the sea, and through the cable they are connected to the grid connection. So we are planning whatever way we could do to extract or use renewable energy source to reduce the grid emission factor. So that is what we call it as a grid 2.0. It is in the planning stage. It will take another 5 to 10 years, but gradually it is moving in that direction. So this shows you an animated picture of the paradigm shift in the grid structure. The top one that you see is the conventional grid. So you have centralized generation, and then you have a demand. So power flows from the generating stations to the demand, unidirectional. But in future, the grid will be much more complex. So you are not going to throw away the centralized power generation. That will be there, but we are not going to build more. What we are going to build more is responsive, distributed local generation. And what I mean by that is renewable one, renewable two. We can have energy storage devices. And as you see the arrow, they are bidirectional. So if we have enough renewable and there is a demand by the load, then renewable supply to the demand through the through the point of common coupling. But if the demand is not there, the renewable pump in into the energy storage, or the demand is more, then we extract from the energy storage. So we will have a responsive distributed local generation. We will have a responsive demand. What I mean by responsive demand is to bring in flexibility in the demand as a building. In the building, we have air conditioning system. So if I can flexibly change the air conditioning system's load, depending on the time, how much of energy I have, then I match the generation and the load demand simultaneously and stabilize the system to run efficiently. So this is what I'm trying to say is that the load has to be responsive, the generation has to be responsive, and the utility grid also has to be responsive. So all this thing is possible provided we make it more complex, more intelligent, and having sensors everywhere. And in real time, we control the power flow to stabilize the whole system. That is what we are talking about, the microgrid or the talk that I'll be presenting today. When you say that you can use renewable energy sources, they bring in their own problem. For example, this top graph shows the mean output from photovoltaic panels placed in the Changi area. So it is fluctuating mean output in terms of kilowatt. So the challenges of temporal, spatial, and structural variation when you are using PV. The bottom one shows the Changi Airport and the Terminal 5, which is the future Changi Airport that is being built. We are trying to tap renewable energy sources. And if you see the white color cloud over here, that white color cloud, let me just get the laser pointer. Yeah, that cloud over here will have its shadow on the ground. And if your solar panels at the bottom is there, then the power output from the solar panel will drop. Then how do you meet the load demand? Do you start up another generator? The answer is no. In Singapore, the solar radiation is quite diffused in the sense that clouds come in and go. So you must make sure that the cloud is not going to stay there, but if you have an energy storage, you can pump in a certain amount of active reactive power through the power electronic converter and stabilize the system, because no point in starting a generator, because you know that the cloud is momentarily coming in for few tenths of second and then it will disappear and the solar panel will again produce power. Then you reduce in real time the power drawn from the energy storage device and stabilize the whole system. So basically, you need to act quickly and you need to have the precise information, not based on the forecast, but real time information by having sensors and control to stabilize the whole system. So prediction is difficult, especially if it is about the future to predict. But higher flexibility and quickly respond. So basically what I'm trying to say here in this diagram is don't depend too much on the forecasting. Forecasting can have error. For offline design, you do forecasting to design the system, but you must have 20 to 30%, because the forecasting can go up by 20-30%, then you must be able to act immediately by having smaller installation batteries and higher flexibility to quickly respond and stabilize the system. So faster decision, faster real-time optimization has to be done, and transfer power from the batteries into the system to stabilize this thing. And that will lessen the need for spinning reserve, and the whole power generation will be much more efficient. So the diagram that you see here, this is in a bright sunny day, but when the cloud comes in, the whole island, Jurong Island, is covered with cloud. So the power is going to drop drastically during that period. So if you don't have a contingency measure to pump in the power through the energy storage device to stabilize the system, then there could be power failure there. So you must act quickly to stabilize the whole system. So It's the same thing. All these things has to be managed by intelligent machines. A human being operator cannot do in milliseconds. Response time will be too slow for the human being. So all these things must be done in an automated way by having intelligence built in the power converter and control methodology that we have. So grid 2.0 must be able to optimize energy saving, reduce the carbon footprint, maintain grid stability, improve self-sustainability, and also must have the scope to accommodate further structural changes to the grid as time to come by. The demand will increase. So it must be flexible, not that you scrap everything and start building from the scratch again. So when you design, you must have the flexibility to add on more generation in a distributed way. Then that is possible to meet the demand. So real-time power flow management for grid 2.0 has to be done. So this shows you the power flow model using a holomorphic power flow analysis. Our research students, Jaimala and Krishnanand, and we had a paper that won the best paper award. So this is one of the very important area in Singapore called the Jurong Island. This is the main crust. All the industrial refinery industries are there. It is a highly secured area. Nobody can enter there without permission. So this shows you the power generation and the load centers there. This is solved. The power flow solution, holomorphic embedded power flow, is in real time. In milliseconds, this converges, this thing. So as you can see, some of the transmission line at the northern side becomes red momentarily. Yeah, now it becomes red. What does that mean is when it is red, that means that portion of the transmission line is getting stressed or overstressed. So by having in the command and control station through the GIS system and graphical user interface, if you do, you can see in real time what is happening. So this is something like a digital twin of the whole power network. And you can click on different point and then get all the information about that particular load or a particular generator. And then condition monitoring, preventive maintenance, predictive maintenance, all can be built in on the same thing because you have all the data and you can you can take action from the command and control station to delegate the manpower to repair something. Okay? We compared the holomorphic power flow with the conventional power world software. And the point I'm just trying to say, at a particular node, the volt is from the power world, it shows 229.994 kilovolt. And from our holomorphic power flow, it gives the answer as 229.991. So the third decimal point, 991 and 994, the difference is there. So that's not so much of an error. And in real time, we can solve these things. So we have done for 12 bus systems, we have done for 209 bus systems of the IEEE and tested, and it works out quite okay. And we have implemented within the lab scale environment with emulated data, and it works out. So the need for digitalization at the micro or the nanogrid age, demand side management has to be done, how to enable the grid for fast and reliable demand response. So the load demand should be responsive. What I mean by that is it is flexible so that if the power generation at a particular time is not that high, rather than starting off a new generator that will take time, if I can reduce the load at a particular time from the demand, then I can balance the two. And this must be done in real time. And so demand response we implement in Singapore by getting a call from the aggregator and to automatically shut down some of the non-critical load. Still under study, but it is done. So the conventional single source, so the building is used as a consumer from utility, it consumes energy. But The new buildings is a presumer in the sense that you have rooftop solar panel, you have integrated energy storage devices, so you have multiple resources there. And if the building has sufficient, we have one of the building within the campus, which is called New Design, School of Design and Environment SDE4, that is a net positive energy. It is, of course, built from the scratch design so that whatever energy consumed within the building is all generated locally through the rooftop solar panel, and it has surplus so that it feeds back to the grid for the other building to do. So all building within the campus infrastructure will be a net zero, if not net positive, net zero or super low energy consumed building so that we can do the management more properly. There are issues when you have multiple sources, voltage issues will be there, but there are opportunities for digitalized services, optimized operations, smart management. So these are the digitalization of the whole power network I'm referring to. These are not yet there, but it will be coming up in future. We also work on the energy storage for the microgrid integration. So as you know, on the right hand side, on the top that you see, you have the utility grid, and then there is a bidirectional isolated DC to DC converter to interface the grid level energy storage system. So we have a couple of projects funded by EMA to integrate energy storage devices of 2 megawatt hour at the substation level. So I have managed to get a grant to work with the Keppel Offshore Marine on the floating solar panel on the seabed, on the sea water, and the gas turbine. So it is a floating living lab, and we are working on that project to integrate the energy storage devices also. The work that we are doing, so if you look at it on the right hand side here, utility grid, you convert AC to DC three phase, you have the electrolytic capacitor DC link, then you invert to high frequency and then the high frequency transformer, and after that it goes to the AC to DC controlled rectifier to the battery. Our objective is to get rid of the DC link because the DC link capacitor is one of the weakest link that fails, the electrolytic capacitor. And you have two stages of conversion, AC to DC, DC to AC. So we merge these two by using a matrix-based DAB converter. So we convert from low frequency, line frequency AC to high frequency AC directly. And by merging the two converter into one, we get 10% improvement in the efficiency straight away. And then high frequency transformer, and then so this is basically a part of the solid state transformer that we are working on, and we have completed a project in that. This is the electricity consumption in Singapore. I'm not going to go details, but just wanted to highlight that more than 200 megawatt hour of energy storage systems beyond 2025 will be implemented. At the moment, we have about 350 megawatt of solar power generation. That will be increased from 350 to almost 6 times, 2 gigawatt peak by the year 2030. And these are the installation of the solar panels done at different places. The other thing is we are going to go full electric by 2040. So by 2030, we will be implementing 60,000 EV charging points throughout the island so that people get the infrastructure ready so that people can buy electric vehicle or hybrid vehicle. So that's in the pipeline for the electricity consumption. Yeah, this I had already explained, so I skip it. Yeah. Is the grid necessary? That is the question we must answer ourselves. So the left-hand side, you see the conventional generation, demand, matching, unidirectional. Then we have generation. Then we have distributed generation, which is responsive power generation, PV panel, energy storage, flexible demand, all connected, multiple distributed way. Then you look at it, the next futuristic is, do you really need the G? Or can we manage like this one? Then we don't need the centralized power generating station. So all are connected with each other like a grid, except the centralized power generation. So that is what, is the grid really necessary? I don't know. I don't have the answer to that. Maybe it is possible if you can manage all these things intelligently controlled in an automated way fast enough, it is possible to do that. And that is what uh, uh, Dushan Bobridge from Virginia Polytechnic put it up as the energy router. So all energy sources will be connected to different loads and everything through a power electronic converter, and that he calls as the energy router. Then we don't need the grid, all are interconnected. That's possible, probably. And integrate the smart buildings in that domain. We work quite a bit in the building related research. In Singapore, buildings consumes almost about 30% of the total energy. So if you can manage the load demand from the building, mainly from the air conditioning system, which is about 60 to 70%, and lighting another 15, so almost 80% of the energy, if we can control and manage it, then we can save significant amount of energy and then go for net zero or net positive at the building level. Then that will be one of the goal that we are working towards it. So smart grid, open electricity market, demand response. So demand management for these smart building grids. Actually, the Department of Energy in US has already called a scheme called connected communities. So each building are all interconnected. So these are the communities of building. So whenever a particular building has a deficit, then you draw from the neighboring building rather than drawing from the utility grid. So locally, the power is transferred and managed so that the long transmission line, distribution line losses can be minimized. Then can you do, when you have the open electricity market in Singapore, we have 16 different retailers who can provide you electricity. Even the banking people, DBS Bank has gone into the providing electricity to the market player. So everybody is jumping onto the wagon of open electricity market, demand response, and how to manage it. Just like your mobile phone, telcos, you can buy from different Airtel or from, I don't know, Ambani's or other thing, Reliance, all these things. So you can buy electricity from different supplier, and they owe the customer by providing discounts and all these things. So some are successful, some are bankrupt, but it continues basically. This is the Singapore Green Plan 2030, basically on the national sustainability movement. And I don't know in India whether you have or not, but in Singapore, we have put a carbon price. So there is a tax for over consuming energy. And the carbon tax is about $5 per tons of CO2 emission. And that 5 by 2034 is going to $25, by 26 $45, by 2030 it could go as high as $80. So all the big energy consumer are now planning for this carbon tax and make it more green so that they don't have to pay the tax. And Singapore goes by the way that there is no subsidies. You have the funding or the money available, you go and utilize it, but pay the tax for that one. And that is how it goes in Singapore. With that, I think I stop it here. Then I go to the main. So that I gave you the overview of where the grid is going towards in future. How am I doing the timing?
Next 1 hour, so 4 p.m. India time.
Okay. So how much more time I have?
Half an hour. I guess I'm
Okay,
in 8:50.
fine, fine. Half an hour is more than enough. Yeah. So now I'll go to the power converter for microgrid application. So a typical multibus microgrid systems, this diagram that I saw, actually this work was done by one of my PhD student from India. His name is Sobhik Dasgupta from West Bengal. He worked for me around 2010 to 2012, around that time. Then he has, of course, graduated and joined Rolls-Royce in Singapore. He was working, but now I think he is moved to Germany, working in the microgrid area of the research. So, excuse me, I'm presenting his part of the work here. So a typical multibus microgrid system, if you look at it, this work was done in 2012. So it's almost about 10 years back. But that time it was too futuristic, but it is now implementable at that level, at the grid scale level. So at the top, you have the utility grid. There may be some loads there at the medium voltage AC level. Then you have a step down transformer, and then you have a static transfer switch, which is basically on and off to connect to the grid mode or islanded microgrid mode. And then you have the common bus over here. Then from the common bus, you go down through the transmission line, and then you'll have the local bus that I'm showing you through my laser pointer. So this red color one shows you a distributed generation one. I can have multiple distributed generation, DG2, DG3, and they can have different types of resources. It could be a renewable energy resource with power converter. It could be a diesel generator with a DC to DC converter, or it could be other energy resources, wind or something like that. And you may have a local storage devices connected there. Then they are connected. Let's focus on DG1. They are connected through a inverter to the local bus, and the local bus may have critical load. And then on the common bus at a higher voltage level, they may have a non-critical loads like this way. So multiple distributed generating systems all put together is called as the microgrid. The microgrid can be in grid connected mode through the static transfer switch, or it could be operated in an islanded mode through this switch over here. Now, what are the issues? The main concerns for the microgrid research at that time, or even today also it is equally true, is we need a high bandwidth active and reactive power flow control to the loads, critical loads or non-critical loads. Then we must do total harmonic distortion control of the current that you draw from the utility grid at the common bus side. Then load voltage regulation has to be done. So these are the main research focus area at that point of time. Now let me tell you, when it is grid connected mode, the voltage is synchronized with the utility grid. So all these inverter through the DGs are all operating in current controlled voltage source inverter mode. So DG1 is operated in the current controlled voltage source inverter, CCVSI. Okay. So they are injecting a certain amount of active and reactive power into the grid. Then who maintains the bus voltage? That is being maintained by the utility grid, because that's the infinite bus we talk about. Okay. So now we'll focus more into this red color box, DG1. So the inverter, I'm talking about single phase now. I didn't say what type of inverter. It could be three phase, it could be single phase, but I'm talking about at the distribution level, single phase inverter. So single phase parallel connected inverter. What do I mean by that? I'll explain in a minute. Yeah. So the inverter that you see here, grid connected parallel inverter, is connected in parallel with the grid. And then both this grid and the inverter both of them in parallel connected to the critical load. So when I say it is a parallel connected inverter, what I mean is the renewable energy source with inverter is connected in parallel to the grid, and both of them are connected to the load in parallel. Okay? So that is the parallel connected inverter. Now, you look at it, the conventional scheme. You have renewable energy sources, you have a DC to DC converter to, to get the MPPT, and then you need to step up the voltage from the solar PV panel, if it is a PV panel based, a DC to AC inverter. And then you connect to the load over there. And the load is also connected in parallel with the grid. Are you all okay? Now, we also have another inverter, traditional one, which will provide you, you have a DC source. Let's not worry where from it is coming, but you have a DC source and you have a converter to convert DC into AC. And what is the role of this one? It is reactive and harmonic power compensation scheme. So if the load is nonlinear, it is going to draw nonlinear current. That means the fundamental current plus the harmonic current. Now, if you draw the harmonic current along with the fundamental current from the grid, your ITHT of the current would increase significantly. Get my point? So if the RMS current goes up, I square R loss on the transmission line goes up, and that's not desirable. That is why harmonic compensation we provide through another converter locally. And if we do not have enough renewable energy source to meet the load demand, we just draw the fundamental component of the power from the grid. All the harmonic current are supplied locally through these resources. That's the whole idea, conventionally done. But what is the drawback here? Drawback is I'm using one, two, three converter. Fortunately, I don't put another converter between the grid and the load, because I can control it intelligently. Objective here, or rather the student's objective at that point of time is, can I merge this inverter and this inverter into one? And this DC source can come from here. Then I reduce the cost and the losses are minimized. So I improve the overall efficiency and at a lower capital cost. That's the idea that prompted us to work on this, and can I merge these two into one? There are different possible solutions. So Freddie Blabjerk and others have proposed DQ frame based proportional resonant controller, blah, blah, blah. I'm not going through go through the details, but there are drawbacks of each and every scheme. And that is what we are trying to overcome. The last one is a current controller. So they used a hysteresis current controller with constant switching frequency, but then the ripple increases. Or you go for a variable switching frequency, then your losses increases. But the current is going to be highly nonlinear if the load is highly nonlinear load. So we see how we can propose a advanced current control scheme so that we overcome some of the drawback of the previous research. Then Shu et al. Proposed positive and negative sequence DQ frame PQ theory based unbalanced grid connected inverter, and that has its own limitation. Special repetitive controller we proposed, but it has certain dynamic response, certain problem like dynamic response is relatively slower, but we have used it along with other controller. Please escape it. Yeah. Now pay attention here. I have a renewable energy extractor, be it solar panel, be it fuel cell, or be it a wind, whatever it is. So you extract the maximum power point through the power electronic converter, and then you get the DC bus. You may have a storage or capacitor, whatever is the DC source over here. Now that DC is converted or inverted back through the grid connected parallel inverter to provide you the inverter voltage, V inverter. Now this V inverter is connected in parallel with the grid, and both of them are connected to the critical load over here in parallel. Am I all clear? So the load requirements is PL plus JQL mathematically, and this PL plus JQL can come from two sources, either coming from the inverter or coming from the grid or coming from both the sources in a hybrid way. All clear? Now pay attention, the student. You know Kirchhoff's current law, right? Kirchhoff's current law at this node, IC, that is the inverter current, plus the grid current is equal to the load current. Remember this. Load current comes from renewable energy source based inverter, IC, or from the grid. These are the two. Okay. So I can summarize that the total active load power PL is shared between the active power from the inverter and active power from the grid. And by having inverter power, we reduce active power drawn from the grid, and therefore we have saving in the power consumption from the grid. That is one idea. The current drawn from the local bus, that means the IG, must be a pure sinusoidal with a unity displacement power factor. The current that the inverter must inject IC is highly nonlinear, time varying. So a linear controller like PI would not be able to do the job. So we go for a nonlinear control, Lyapunov function based control, to control the active power flow between the grid and the load and the inverter, and also the current that we draw from the grid, its THD control, total harmonic distortion, and wave shaping is done. That part is also done through the control of the inverter. Remember, there is no controller between the grid and the load. There is only one inverter. So we can only control the inverter current IC. And indirectly, that will control the current drawn from the grid for a given amount of active and the reactive power need. So this is published in IEEE Transaction and Power Electronics in somewhere 2011. There are two parts. This is the parallel, and the following one will be series one. I don't want to go through details of the thing, but what I'm trying to say here is that PQ theory is typically applied in three-phase system, but we have extended that to a single-phase system. So we put the voltage phasor as VGR, real, and VGI, imaginary voltage, fictitious. So your apparent power SG is VI conjugate, and if you do some analysis on that one, that will give you ultimately this equation, that the grid reference current, which is aligned to IGR, is given by this, and this is VGR, VGI. So I need to monitor the voltage with a voltage sensor and extract VGR, VGI. Then I also need to know how much of power I must draw from the grid, active and the reactive power. If I know this thing, I can compute IG in real time. If I know IG, what is that? Yeah, IG plus IC equal to IL. Then my objective is to control this inverter in the current control voltage source inverter. So I must know what is the current I must inject into the load IC. So IC star is IL minus IG star. IG star I obtained from this equation. Substitute here. And I'm assuming that I can monitor the load current through a sensor, so I can get IC star. Once I know the reference current for the inverter, then I come up with a current control scheme to realize this current IC to be following IC star. That's the whole idea. So you monitor, rather measure VZ from a sensor that is equal to VGR. You have a 90-degree phase lead all pass filter to generate VGI. You need it. The grid power, active, reactive, and you use that equation to give IG star, and IL, if it is measured, IL minus IG star is IC star. So this is how you get your reference current for the inverter control. We use a Lyapunov function based current controller to track the reference current. So as you know, your state variable X is IC. So we put it X dot is equal to Fx plus Bx U plus D. D is the disturbance term. So this disturbance can be the grid voltage disturbance or the inverter disturbance, like the blanking time that you have in the inverter, all can be put together as a disturbance term, and we can estimate this disturbance to control the system. So this is a simplified inverter, then the line choke, and then the grid. This is how the whole system is connected. The load is somewhere in parallel, not shown over here. So Lyapunov function, we choose the error is xd minus x. The function is v is equal to half e square. Then from there you get the control signal ut, that is from this equation. And if I substitute this control in this one, then that gives me dv by dt is minus lambda e square. Or you take it to the other side, it will be plus lambda e square. So solving this differential equation by choosing a proper value of lambda, the error can be converged to 0. That's the whole idea here. Okay? Simple mathematical analysis to come up with the control methodology. And special repetitive control is employed to estimate the disturbance term D. Okay? So in block diagram, your reference current comes in here, your current sensor gives you IC, all the gain and everything anti-aliasing. So you get the error. Based on the error, you compute the control using the Lyapunov function based control, ULF. Same error is put into the special repetitive control to give you U special repetitive control. So this is a dynamic control. This is more at a steady state, but both combinedly gives you the control signal. This part is simple sine PWM scheme and the current control voltage source inverter getting signal. That's standard thing. The question is, how do you come up with this gain lambda? So we have a mathematical analysis, knowing the disturbance maximum and all those things. I can come up with the lambda value so that the error converges eventually. This is the overall block diagram representation. So we monitor, we sense the grid voltage, the load current, and the inverter current. So these are the sensor. And then you put it back into the control scheme. Now I'll show you some of the experimental result. We are using a highly nonlinear load, which is a rectifier load. Remember that this is implemented in the lab scale level. So the students are always afraid. Even when I was a student at BHU, I was also afraid not to blow up the system. So our idea is to implement the control scheme irrespective of power level. So he has gone for a low power level, 35 watt load. The grid voltage is 50 volt RMS. On the left-hand side, what you see, the top graph is the inverter output voltage, instantaneous value, the high frequency signal at the pole point of the inverter. Yeah. The bottom one is the grid voltage. We assume the grid to be perfectly sinusoidal without any harmonics. And it is at 100 volt per division. The load is highly nonlinear rectifier load. So the load current is peaky because of the capacitor filter like this. Now I assume here that the grid power requirement is 0. So P and Q. Q, I assume reactive power is 0 for unity power factor operation, and active power requirement at this point of time, I decided that let it be 0. That means my renewable energy source based inverter current IC has enough power to meet the load demand. So the same load is here IL, same grid voltage, And now you see the third one, this one is the inverter current IC. Remember the Kirchhoff's current law I said? IC plus IG is equal to IL. So IG is 0. Why? Because PG is 0. So IG plus IC is equal to IL. And it is the inverter is able to meet the load current demand. Am I clear? Now let's go to the next slide. So I'm repeating this slide here with 0 grid power. But then let's say it is a solar panel at a particular day, the sunlight is not there, and I am not able to meet the total power of 35 watt coming from the solar panel. So the inverter can only supply 5 watt, but my load demand is 35 watt at 50 volt. I must meet. So 35 minus 5 grid power is 30 watt. So under this circumstance, you see now the same load current, but only only 5 watt is coming from the inverter. The rest 30 watt is coming from the grid. So for that 30 watt, the grid current you see in the top, 1.7 amp peak to peak, which was 0 in the previous case. Clear? So this grid current, instant to instant, plus the modified the inverter current is equal to the load current. I pause here. So this inverter current is supplying only 5 watt of power, and this grid current is supplying the 30 watt, and this is the grid voltage. Please note that the current drawn from the grid must have only fundamental component. So that is why you see the grid current is almost close to sinusoidal. It has very little harmonics, but the load current has significant amount of harmonics. So the harmonic part of the load current is being supplied locally through the inverter and part of the active power also. Plus the rest are being drawn from the utility grid at unity displacement power factor. So this is the current zero crossing. This is the voltage zero crossing. They are matching. So the displacement power factor is maintained at unity. And remember, I do not have a controller between the grid and the load. All is done intelligently at the inverter control. Since load current is inverter current plus the grid current, once you fix the inverter current, automatically the deficiency will drop from the grid. And since harmonic part of the load current is coming from the inverter, only the fundamental part of the current to a certain extent, the active power requirement plus the harmonic power is coming from the inverter, and the other part is drawn from the grid 30 volt. And that is possible through intelligent control of the converter, basically. Yeah, this is that disturbance terms, B error, the special repetitive control part. It's trying to say that D cannot use a sensor. So in real time, you need to put a repetitive control. Repetitive control takes care of periodic disturbance. So whatever periodic disturbances are there, that repetitive control provides the control signal, complements the Lyapunov function based control, and take care of the disturbance part of it. Now what I showed you here are all steady state. Now I show you a dynamic response. So at this point, I changed what? Yeah, this is the zoomed view. So we sudden change in the grid active power from 0 to 30 watt at this point. So this was 0, except the noise part is there. Then here it is 30 watt. And corresponding inverter current drops from this to a lower value. But the load current, you see, even if at this point disturbance is created, it is not affected significantly. So this part, no power is drawn from the grid. Here, 30 watt and 0 var is drawn from the grid. So this shows you the transient response of the system. It's the same thing, 10 watt to 30 watt. So various tests we have done just to say that the system is, control scheme is stable for transient operation or disturbances. Then we change the grid voltage from 40 volt to 30 volt RMS. If you see here, this is larger 40 volt, then it is smaller 30 volt, and the whole system is in stable operation throughout the operation. So with that, I summarize this part of the work. The proposed single-phase PQ theory-based approach ensures easier control of the grid active power flow or reactive power flow. In our case, we assume reactive power demand is 0, but you can put it whatever Q you want. The proposed Lyapunov function-based controller is relatively much simpler compared to the other, the, what do you call it? The DQ in the positive and the negative sequence for the unbalanced harmonics and all those things, that type of controller, or multiple PR resonant controller. That becomes more complicated. Lyapunov function-based control, the mathematics that I showed, is straightforward and easily implementable using any of the digital signal processor. We use a disk space-based system, but any Texas Instrument DSP will be able to do that. The proposed controller provides better tracking, enabling single inverter doing both the power flow control and the power factor correction, both at the same time. So the two inverter we merged into only one inverter. That's the gain that you have. So that's all about the parallel connected inverter. I have only about 5 minutes. Let me finish the other part. What is the issue with the parallel connected inverter? Majority of the inverter we connect is basically in parallel with the load and with the grid. So what is the problem? The problem is if the grid is corrupted at the point of the common coupling, then your critical load will see the same corrupted grid voltage. But if your load is sensitive and if you have a harmonics in the grid voltage and your critical load cannot tolerate that, it may trip the supply and disconnect it. So how do you improve the parallel connected systems? Can you improve the grid voltage? No, this is infinite source. You cannot control that one. So how do we resolve this problem? This problem can be resolved if you don't connect in parallel, you connect the inverter voltage, V inverter, in series with the grid. And that is what is the series connected, the second part of the paper. So it is series connected inverter to overcome some of the drawback of the parallel connected inverter. So this part remains the same. So this is inverter output voltage. So inverter output voltage is connected in series with the grid voltage. And grid voltage plus the inverter voltage together meets the load voltage. So our objective is to make the load voltage regulated, constant at the desired 230 volt RMS level, irrespective of the grid voltage, sag, swell, harmonics, anything. Are you getting my point? As you know, in India, I left India about 40 years back. The grid voltage fluctuates quite a lot, isn't it? 230 volt can go as low as 160 volt some places, or can go as high as 260 volt also. So at home, if you have critical load like computers, like fridge, like air conditioner, what you used to do, maybe being used to do now also, is to use a voltage stabilizer, isn't it? So your incoming voltage 230 volt has a sag swell. You put a voltage stabilizer, you add voltage in phase or out of phase, depending on the voltage, grid voltage variation. So For multiple load, you'll have multiple voltage stabilizer, like one for air conditioning, one for computer, one for fridge, you name it. Okay. So here the point is, why have multiple voltage stabilizer? uh, why not stabilize the incoming voltage? That is what we are trying to solve it here. And we were aware of the problem in India and China. This problem still exists basically. So when you connect in series, let's see what happens. Remember, the inverter voltage V inverter is vectorially added with the grid voltage to control the load voltage. We are not controlling inverter voltage in phase or out of phase with the grid, but we are adding it vectorially. I'll explain that. This is your grid voltage. So grid voltage, load voltage VL is the requirement to be maintained constant at 230 volt RMS. My grid voltage can go higher, lower, sag and swell. So I produce my inverter voltage in such a way that grid voltage plus inverter voltage always meets the load voltage requirement. Agree? Now, let's say most of the loads are what? Lagging power factor load or leading? It is lagging power factor load. So the load VL is here, IL is here. So the power factor angle IL is lagging the supply voltage by an angle theta. So that's the power factor angle cos theta. And it is a lagging power factor load. All agree? But the load current IL, give me a minute. The load current is also flowing through the grid, is also flowing through the inverter. So IL, IG, I inverter, they are all the same, isn't it? So let's compare with the grid voltage. So the same load current with respect to the grid, is it leading or lagging? It is leading by an angle gamma. Got it? So how does a lagging power factor load acts as a leading power factor load at the grid side by this control scheme? So indirectly, the inverter is acting as a VAR compensator. Get my point? So we will see. And how to calculate this gamma angle so that I can place the IL with respect to VG at this point is come up with this inverter power requirement, a mathematical formula, so that can compute. If you know the grid voltage, the load voltage, and the inverter power, then I can calculate gamma. And then I can place the vector IL with respect to the grid voltage like this. So that's the whole idea. Um, this goes through. So the requirement is that the load voltage V peak with a multiplier with the cos phi becomes VL, the load voltage sinusoidal waveform, time varying. And you measure from the voltage sensors VL, you get the error signal, and you use a special repetitive control to control the inverter there. And of course, you will have the grid voltage, VG comes in, that calculates the gamma from here. You have the load power factor angle theta and the phase lock loop beta. So all these things put together becomes phi. Yeah, over. Okay. That's the angle phi that is shown over there. Yeah, special repetitive control is over here, but this is a slow response. It is only applicable at steady state. So you must have a dynamic control, like in the parallel controller, parallel connected inverter, we had a Lyapunov function based controller, but here put a simple proportional controller KP. So these two add together becomes the total control voltage. Now, what is the special repetitive control? It was actually proposed by Tomizuka from UC Berkeley for robotic control, pick and place. So robot, when picks up an item and places it on the grid. No, my apology, not grid, on the PCB placement of the component. First time it does a mistake. It learns, second time it improves, third time it improves. So you control cycle by cycle. Then you can improve on it. So you look at the control voltage. It is special repetitive control is nothing but an integral control. But you don't integrate sample to sample. You integrate cycle to cycle. So the present control at ith cycle at the kth instant theta k is equal to the previous control USRC at the I minus 1th cycle at the same sample point theta k plus again k SRC multiplied by the error signal. So first cycle, I have some error. I improve the controls for the second cycle. I reduce the error. Third cycle, I reduce the error. Eventually, few cycle, the error can be reduced almost close to zero. Then it becomes a feed-forward signal. But in power systems or the power electronics, because things are changing dynamically, you cannot do a feed-forward. It has to be a closed-loop feedback system. And we do that one. And how to come up with the gain K SRC, there are mathematical derivations for that one. Now this is the last few part. Pay attention here. Yeah. The nominal voltage is 110 volt AC at a power frequency 50 hertz. RL load, passive. Load power is 77 watt. And you see here at the bottom, the red curve is the grid voltage. Our voltage requirement at the load is 110 volt RMS, but the grid is 90 volt. So there is a sag, 18% grid voltage sag condition. So this grid voltage and the inverter produces at the top, the inverter output voltage VI. So VI plus VG becomes VL. So VL is maintained exactly at 110 volt RMS. The theta angle, lagging power factor angle theta 18 degree at the grid side, gamma is 63 leading. A lagging power factor load is shown as a leading power factor, leading current drawn from the grid side. So this is under 18% grid sag, and here we have a swell 130 volt, but the load voltage is always maintained constant at 110 volt. So sag, swell, both can be taken care of. How about harmonics? Now we inject the harmonics in the grid through our programmable power supply. So I have 36% dip in the fundamental grid voltage, 50% third harmonic corruption, 30% fifth order harmonic corruption. Then if I use only P controller, that means not the special repetitive control, the load will see a corrupted voltage like this. That may not be acceptable. So this part, which is VL star minus VL, the error signal is pretty large, 20 voltage per division. Only proportional controller is working. The error is too large. The moment I switch on my special repetitive control, this error is brought down to less than a few volt over there. And this load voltage for the same operating condition of the grid voltage now improves this green color to this green color. So this voltage is almost perfectly sinusoidal. No harmonics are there, and load voltage is maintained constant, pure sinusoidal. And the inverter voltage is highly distorted. So VI plus VG is equal to VL. And of course, the grid current IL for a passive load 18 degree phase lagging. Yeah. We also tried same thing for grid frequency changing from 50 hertz to 45 hertz. It works perfectly okay. You don't need to resynchronize. Proposed SRC is robust enough to tackle the auto synchronization property of the grid frequency changes. So to summarize, taking a little bit more time, uh, the proposed control strategy of the series inverter stabilize the load voltage, whether it is a sag, swell, or harmonic distortion. The proposed SRC makes the control strategy grid fundamental frequency independent and uh, ensures, the strategy ensures that the leading power factor, even if it is a lagging power factor load, at the grid side, it shows as a leading power factor load. So one controller, just like they say, you buy one, get two free, the cell. So you buy one inverter for renewable energy source extractor, but you get voltage stabilizer as a free. You get bar compensator as a free. You get harmonic compensator as a free. So you buy one inverter, you get four. So one you pay, three you get free. Thank you very much for your attention and appreciate it. I'll be more than happy to answer any question. Let me switch on the light. It has all become dark.
Yeah.
Uh,
Thank you, sir. Thank you for a very wonderful, informative lecture. Our students and participants have typed their questions in the chat box. I request all of you to turn on your cameras. We will have a group photo then before vote of thanks. So, sir, there are questions in the chat box if you can read it.
yeah, let me see. I'm sorry, I'm not able to see.
Yes, I'll read it maybe. So, there is one question from Azra Malik. She is asking here the grid connected parallel inverter operation consists of grid and inverter in parallel supplying to the load. What is the scope of multiple inverters in grid connected PV system operation? How does that affect the connected critical loads?
Um, yeah, the grid is connected. The inverter is connected in parallel with the grid. So the question is, if you have multiple inverter from multiple PV sources,
Yeah.
all of them still can be connected in parallel with the grid to meet the load demand. Now, the again, you have more than one. We haven't tried it out, but I don't see why it should not work. So your controller, if you design accordingly with intelligence built in, then your total load demand may come from inverter 1, inverter 2, inverter 3, plus the grid. If inverter 1, 2, 3 combinedly can meet the load demand, no power drawn from the grid. But the control methodology must be changed. We did not work on that one, but it is possible to do that. Sure.
Okay. Thank you, sir. So the other question from Anas Khan, he's asking, my question is that energy storage still remains a great concern, and for an overgrowing economy such as Singapore, it is even more challenging to keep up with the pace. Uh,
Yeah, storage. If I understand the question correctly,
yeah,
storage
pace on
is,
the infrastructure part as far as the energy storage is concerned. How are we making progress on the same?
yeah, you have to design the storage capacity intelligently in the sense that, or optimally, that um, depending on what are the other sources and contingency plan that you have, if n minus 1 contingency plan, if one fails, how the energy storage along with the other sources are able to meet the demand. So based on that, you size the storage capacity. Now, you cannot go to infinite storage capacity because the cost will be quite very high. So the critical part is, how do you size the storage so that under various operating scenarios, it is still able to stabilize the system if there is one failure in the system.
The second part is whether the GIS-based grid model which you shown is feasible to replicate in India in years to come.
Yeah, why not? No, this we did it in our lab under emulated condition.
Yeah,
So if we can do it in our lab, why it cannot be done in any of the
exactly.
lab in India?
Exactly.
You refer to the paper that we have, and that will give you enough background that it is implemented in real time using different microcontroller, multiple microcontroller to meet all these demand. And we have shown, except that these sensor are not directly connected, we have emulated the sensor data and feeding in. But otherwise, the system is running in real time.
Okay.
The problem is you need to do the power flow analysis in real time. You cannot rely on offline because sources are dynamic changing. Load is dynamic changing. So whatever offline simulation or power flow analysis you do may not be realistic in real-time operation. So you need something that is real-time, converge quickly in millisecond, so that you can take control action from the energy storage device through the power converter to inject a certain amount of active or reactive power to stabilize the system.
Okay. The question from Gajendra Singh is asking, what happens when proposed controller-based system is connected to the weak grids? How reactive power is managed by the built-in inverter as it has rating limitations?
Yeah, so of course, if it is in a weak grid and your reactive power requirements are there and your storage has capacity limitation, inverter has limitation. So the NQ that you need to inject to stabilize the whole system, you may have to set something if you don't have enough capacity through the storage and the inverter.
I
So
think
that must be done intelligently so as to stabilize the system.
right, and I think that is the last question from M. Satyanarayanan. He said, "Dear Professor, what type of storage system are being planned in Singapore?"
Is a lithium ion storage system. So we have a redox flow battery also. At the National University of Singapore, we do research in different type. But the commercial version that is implemented in the Port of Singapore Authority is a 2 MWh lithium ion storage system provided by ABB.
And the environmental concerns related to it are taken care. I mean, that's the next
Yeah,
big part.
the storage battery, all these things are put into a container. The container is air conditioned. So you stabilize the humidity and all these environmental parameter well controlled. Without that, it will not work. You cannot put it outside in the sun and hope that it will work. That will not happen. So they have the mechanism from safety point of view also. So everything is within the container from fire safety point of view, that if something goes wrong, it is well contained within the container. So no personals will be affected by it.
Okay, so thank you very much, sir. I think your presentation gave a lot of queries and a lot of ideas. Maybe our students will contact you via email to you
Yeah, yeah,
directly,
perfectly okay.
they can contact me through me. That's fine. I mean, they have your email ID. So before I request our students to propose a vote of thanks, I would like to thank Professor Sanjeev Kumar Panda and also all IEEE GMI student branch, Exicom and other members for conducting this session very nicely and all the participants. So I request everybody to turn on your cameras so that we can have one group photo for our records, and then the students can propose vote of thanks. I request all of you to please turn on your cameras. Lot more to come. Uh, okay, maybe within a minute everyone will come on camera. Okay, so somebody can take the pic from Azra or anyone from IEEE JMI Exicom or screenshot. Okay. Our friends from Vietnam can also turn on their cameras. From Middle East, they can turn on their cameras. I'll be sharing the code which Professor Panda has mentioned for getting free membership of PLS via email to all of you after the session. Now I request Maria to propose a
Yes,
vote of
sir.
thanks.
So finally, we reach the end of this insightful session, and it's a time to express the feeling of gratitude to each and everyone present, especially to Mr. Sanjeev, who took out time for us and made this lecture so informative. I would also thank Professor Ehtisham Haq for his collaboration and guidance. And lastly, to our audience for their participation and patience. Thank you once again, everyone, and have a marvelous day ahead.
Yeah, it is Professor Sanjay. Yeah. Okay. Thank you, sir. Thank you so much.
All
Maybe
right.
next time we will meet physically and we'll have more interaction in our lab with our students.
Yeah, yeah, no problem in that. I hope to the student and everybody researchers, what I talked about, I try to make it as simple as possible, but still you may have some doubt. But so long as 60% of what I talked about has gone through your brain, then that's more than an achievement. Rest 20, 30% or 40%, you need to work on it or uh, ask question and think about it. Then if you have a query, do let me know. I'll be more than happy to answer. Okay?
Okay.
All
Thank
right.
you very much. Thank you, Professor Panda. Okay. Bye bye.
Nice meeting all of you.
Nice
Thank you.
meeting all of you.
Bye-bye.